inviting me to the conference. It's very nice to be here. Okay, so what I will be talking today is percolation and phase separation of run and tumble particles. So the title appears two different things, percolation and phase separation, but I will try to convince that they're related. Okay, so the summary of the talk is here. These three things. One is that critical phase separation transition is associated with a percolation transition. So any phase separation transition in 2 dimensions, the percolation and phase separation happens exactly at the same critical point. In 3 dimensions, in higher dimensions, they are related. Okay, and their exponents are also related. So second thing is that scaling functions determines universality when critical exponents vary. So in a situation where critical exponent of a system vary because of some marginal operators, then how to determine universality is rather by a set of scaling functions which remain invariant even when the scaling the critical exponents vary. Second thing is that third thing is that MIPS transition belongs to Ising superuniversality class. So when this continuous variation and when the exponents vary, but the universality is determined by scaling functions, I call it a superuniversality. So Z2 symmetry breaking is associated with a superuniversality, Ising superuniversality. So MIPS transitions, I'll try to convince you that that belongs to Ising superuniversality. So I start with percolation. It's I think everybody here knows about percolation, but just for completeness, I'll start it. So the problem is that you start with a 20 by, let us say, some square lattice and occupy some sites. So there are 50 sites you occupy and ask a question whether starting from anywhere from the top, can you go to the bottom, like just by connected links. Connected is basically by the neighbors. So from here it stops here because that's the only point. And if you put 100 particles, this is one example. Here you can go up to this. Only here you could up to this. And 150 you still could not go. And by 230 you could actually percolate. And you can see that the number of, the same way, the size of the largest cluster also grows. For example, largest cluster is this one. Here there is a bigger cluster because of this. And here the cluster sizes are bigger. So the maximum, as you go here, it is called a percolating thing, then the size of the largest cluster also grows. Okay, so this is 20 by 20, but if you go to 40 by 40, you can think that this is whatever happens here repeats. So I just connect them, 4 of them. You can see the size of the largest cluster remains same because they are not connecting. There is not at the boundary. But if you do this one, here also it is the same. But if you take this one, you can see that as the system size increase, the size of the largest cluster also grow with the system size. So there is a transition. If you ask a question, is it percolating? No, no. And from here onwards, this is percolating. And this is like, this no to yes, a question like this is a phase transition. Okay? And now we have to look for an order parameter. So the order parameter of percolation is maximum size of the largest cluster divided by L square. This is one order parameter of percolation. And then once you have the order parameter identified, this is the mean of this quantity, and then variance is susceptibility, and you can define other quantities like Binder cumulant and other cumulants. So the transition here, the percolation transition occurs at density, this value. This is still not known exactly, but people know it to a great deal. And the critical exponents are nu equal to 4 by 3. Nu is the correlation length exponent, beta is the order parameter exponent, and gamma is susceptibility exponent. The scale is rho minus rho c to the power gamma, and minus rho minus rho c to the power minus gamma, and gamma is 43 by 18. So this is known. So what we want to do now is that what is the fractal dimension of the spanning cluster? This is something which I would need later. So you have a cluster, like the one which is maybe white here, and then you ask what is the fractal dimension. Thereby, just you ask how S max, the size of the largest cluster, scales as the linear dimension. So S max goes as L to the power D. D is called the fractal dimension. So now you can see that just because correlation length is epsilon to the power minus nu, epsilon is the distance from criticality to the power minus nu, and in a finite size system, xi is replaced by L because the correlation length cannot be bigger than L. So you can say that phi has to be epsilon to the power minus beta, sorry, plus beta, epsilon to the power beta, sorry, this is plus beta. This is L to the power minus beta by nu. So phi is L to the power d. So if you have S max, then it goes as L to the power d. D has to be d equal to dimension in 2 dimensions is 2 minus beta by nu. That is what you expect. So now just one slide to how to determine this critical exponent numerically when you do not know the exact values, is that you calculate the 4 moments of this stochastic variable S max, k equal to 1 to mean, variance, and Binder cumulant. Binder cumulant is defined by 4th moment, 1 minus 4th moment with 3 times second moment square. So this from this you determine the critical point, like, because this is independent of system size at the critical point, so they will pass through here. So you find a critical point here that is 0.592, which you know here for ordinary side percolation. What is that? No. We'll discuss it later probably, but it's not needed here. So all I want is that they, at the critical point, they cross at the same point. So that is the critical point. So once you determine the critical point, and you can, that is epsilon L to the power 1 by nu, that is a scale invariant quantity. And Binder cumulant is independent of system size. So there is no scaling here. So these are the scaling of Binder cumulant and order parameter scales like that, and susceptibility scales like that. So you get critical point from here, and once you know the critical point, you know epsilon, and this one has only one fitting parameter 1 by nu, so you get 1 by nu here, and then this x-axis now you know, and you get beta by nu from this scaling, and similarly gamma by nu. So 3 exponents you can very clearly get through this. This was everybody knows. Just take one. Okay, so percolation also forms a universality class. So you can go to, instead of square lattice, you can go to hexagonal lattice and other lattices. And instead of side percolation, you can think of what you call bond percolation, right? I mean, and so all of them has this behavior. Fractal dimension is 91 by 48, 2 minus beta by nu. Okay, so these, and they also satisfy hyperscaling relation. This is it's a geometric phase transition because you don't have a dynamics here. You just throw particles and look at the cluster properties. It's a geometric phase transition. So side percolation is a dynamical phenomenon. Okay, so now let us try to think of how a percolation can be thought as a dynamical phenomenon. So you take a lattice, square lattice, and there are particles which are here. And let us say that there is a dynamics which is 1, 0 goes to 0, 1. It's just a simple symmetric exclusion process. So particle just, if there is a vacancy, particle move forward and backward in the same rate. So, and only interaction is hardcore interaction. So two particles cannot occupy the same site. So in this one, you know that all configurations are equally likely. And now if you ask what happens to the largest cluster here, because now all configurations are equally likely, and you know that exactly same point you have a transition. So this order parameter will show a phase transitions at this density, if you change density. It's a dynamical one. Now you can ask what happens if the particles are interacting. Okay? So one of the simplest interaction is the nearest neighbor attraction. It's like Ising interaction. So if you have 2 particles when they are neighbors, I and j are neighbors, so 2 particles which are neighbors has a energy minus u. For example, from this the contribution is minus u, and this and that do not contribute anything. Okay, so only nearest neighbor interaction, and the dynamics is that 1, 0 goes to 0, 1, particle move forward or backward, like to the nearest neighbor if it is vacant, and the rate is 1 e to the power, minimum of 1 e to the power minus beta delta. This is the Monte Carlo rate. So when beta is, temperature is infinity, then this is 1, and which means that infinity temperature, this is the simple percolation. Okay, I'm looking for side percolation. So this problem for temperature or u equal to 0 or t equal to infinity, this problem is simple percolation problem and with the same exponents. So now question is, what will be the critical exponents here? And it turns out that exactly when you put t equal to 1 and keep density equal to half, and then if you change u, then at this value, which is the Onsager value, exactly at the same point you have a percolation transition. Okay? So this is the same point where a magnetic phase transition also occurs. And this model is lattice gas. Okay? This is exactly the same point where the phase separation also occurs. Okay? So let us look at this connection to phase separation. Before that, let us look at the fractal dimension. Fractal dimension here would be 2 minus beta percolation by nu. And beta percolation here is 5 by 96, not 5 by 36. Okay? So this is a different universality class. This is not simply, simply the Ising behavior. Okay? So now what we want to say that this kind of interaction percolation belongs to a different universality class. Let us call it from now on Z2 percolation.
But hold on, I didn't understand how you define the model. So you throw at random because you have an energy. How do you do that?
So you have a fixed number of particles in the one that fix the density. Given the density, T is set to 1, and with this dynamics, you move particles. And thereby, you go to a steady state. In the steady state, you find out every configuration has some cluster which is the largest. Keep a record of this and square of this, and then you can figure out what is the order parameter. Kawasaki dynamics. Kawasaki dynamics.
You see the difference with the normal standard lattice gas?
Yes, this is the standard lattice gas.
Okay.
Lattice gas, I'm saying that lattice gas you study phase separation transition, it occurs exactly at this point. I'm saying that on lattice gas, if you study percolation, if you study, it also exactly at the same critical point. The exponents are different. This is exact means exact. As exact as it is here. UC is exact. So this is the, okay, I'll come to this. Why it is, because that is the conserved and non-conserved Ising model has the same one. And this one, if you just define Ni equal to Si plus 1 divided by 2, then this will create, I think it's far away, but I'll somewhere, I have it there, I'm sorry. I don't know. Yeah, here. So here. So if you replace it Si plus 1 by 2, then this will generate a Si as a term and a field term. Both of them depend on U. So if you put H equal to 0, which correspond to density equal to half, the critical point is same. This is the argument. Ising model lattice gas is the same critical point. Okay? Okay, I'm sorry. I'll go back. Okay, I will not go that far, I think. Okay. So what I want to say is that in lattice gas, percolation and phase separation occur at the same point. The exponents are different. Okay, as you are saying that this is a simple one, that at the same model, you have a phase separation transition also. So here what we plot is that temperature versus density versus temperature. So T less than Tc, this is the same value, U divided by this. And just because I put T equal to 1, U is just this much. So T less than Tc, the system has two different densities. One is gas density, one is liquid density. So this is a coexistent region. Okay, so below this, given the density rho equal to half, T less than Tc, you have a coexisting thing here. And this coexistence disappears at rho equal to half and T equal to Tc. So that's a critical point. And that has exponents 1, beta equal to 1 by 8, these are Ising exponents. But at the same point, what I find is that percolation exponents are nu equal to 1, beta equal to 5 by 96. This is neither Ising exponent nor the ordinary percolation exponent. But is there a relation between them? So percolation and the phase separation occurs at the same critical point, and there's a generic feature in 2 dimensions. We'll see it also later, and but with different critical exponents. So now we ask, this is the same point. Now if you go by the scaling exponent, what is the fractal dimension? So the fractal dimension could be d minus beta by nu, where beta and nu are Ising exponents, or whether it is percolation exponents, beta percolation by nu percolation. Okay? So the answer actually is, this is the correct one. So which means that in Ising transition or the phase separation transition, there is one critical exponent which cannot be determined from beta, gamma, and nu, and that is D. It is not solely determined from the known Ising exponent, and there is extra parameter here if you go by this, D minus beta by nu into a factor 5 by 12, and it is known that, again these are the works, W equal to 5 by 12 for Z2, and these are the numbers for Z3 and Z4. Okay? So phase separation transition occurs at the same critical point, but the exponents are not the same, they're different universality class, and the relation is well known. That is because there is a 4 factor which comes by 4. 2.269, 1 by 4 by 2.269. No, but that is coincidental. Here it is exact. It's proven. Okay. So now why exponents differ is we can say that there is the fractal dimension is an independent exponent, and it carries the extra factor W through Ig. So now question is that how sacred is W equal to 5 by 12 when it is Z2? So if you look at Askin-Teller model, which is a 2-layer Ising system, so there are 2 different kind of spin on a square lattice. One is sigma and one is tau, and the interaction between them is this four spin interaction. And it turns out that lambda is a marginal parameter, and when lambda varies, the critical exponents also vary. So there is a line, this equation of this line is known exactly. Did I write it? No. Maybe here. Here. This is the equation of the line, and all along the line, lambda, this axis changes, and here critical exponents are different and given by these numbers. And there are 2 different phase transition occurs. I will not go to the details. There is one is electric and one is magnetic. And for both of them, if we checked that, so we checked that beta, this W, which is 5 by 12, is the same. So the relation all along the line, so you have this exponent which is beta E, you multiply by 5 by 12, you get the percolation exponent exactly here. Okay, so this relation is valid all through. So this is a very sacred thing, and 5 by 12.
About the Kertész line, is related to them?
Which one?
So if I remember correctly, there was this concept of Kertész line so indeed when you have percolation, but this was not, well, okay, maybe.
This is a different model, we can maybe discuss later, Okay, so now the point is that we can see that there is a relation between phase separation transition and percolation transition. They, at least in 2 dimensions, they occur at the same critical point. So can we exploit this fact to study phase separation transition, which is generally hard to study? Okay, so question is that we'll rather study percolation, which is easier, and infer about the phase separation transition. So what is the summary so far is that you have Ising model. There is a magnetic transition occurs at Tc equal to here, and then this is non-conserved dynamics. If you take a conserved dynamics like Kawasaki dynamics, you have a phase separation transition at density rho equal to half. This part is critical. Otherwise, you have a coexistence thing here. And at the same point, at this point, you have a percolation transition where exponent of this and exponent of this are related by scaling relations. But W is 5 by 12, and rest is determined by scaling relations. So now this can be exploited to study phase separation transition, and that's what we want to do. So now phase separation transition. So you have a coexistence line like that, and you have a critical point here. So now question that how do you know what is the critical point? So one of the way to study, one point is to study is that at the critical point, there is a rho density of liquid and density of gas disappears. So you look at, so if there is a density of liquid and gas, then the distribution of particle numbers at different parts, smaller parts, will have a double peak. And exactly at this point, you have a single peak. So you try to figure out where it becomes single peak. Then that's the first critical point, this point. This is one way. Other way, it is very recently by Binder and group of people in 2018. So you take a lattice which is rectangular, then the cluster, when it forms, it forms by hitting the shorter length. And then you place a boxes which are of size L by L at the near the center of mass, and other L by L boxes like this one and that one far away. So this one will give you the high density, and this one will give you low density, and this one you are avoiding because this is boundaries. So that is the way raw liquid and raw gas you determine, and these points, and slowly you come to this. But doesn't matter which you do, coming here is very difficult, very hard to calculate. So now we want to study the same thing using percolation as a percolation phenomenon, because when you see clusters, that something is making clusters, like there was this talk. So all you are looking for here is actually clustering, something clustering. So if you just look cluster properties, you might get the information about phase separation transition. So we go there again. So we take the Ising model, lattice gas, and now we want to make it active. So what you do is that you have a dynamics which is the same dynamics as Kawasaki model, but then the dynamics is that you randomly choose a site and then choose a particle and then try to move in any of the direction and see if it is vacant, and then you move it. But when you choose a particle, you can go to any direction. The choice can be any direction. So now what you do is that the particles you assign a predefined direction. So there are 4 different particles. One is east, west, north, and south. So those which are assigned east, they can only move to east, and those which are south, like that. That's the only change which I did. And then with a small rate, W by 3, they can also switch. North can become any other things with some rate. So the dynamics is just this run dynamics, which particle move, and this is this dynamics. So now question is that Ising model or lattice gas with activity, what will happen? Okay. So now all we want is that rho equal to half. We take rho equal to half, and when omega goes to infinity, omega is infinity, which means that the particle, this one, can arbitrarily become one of them because this flipping occurs too fast. When flipping occurs too fast, then first direction, before it moves again, the next direction, there is no correlation. So omega goes to infinity. This model is exactly lattice gas model, and JC is the same thing which you know. At this point, you have a Ising transition. So the question which were, this is the dynamics. So basically, if the particle is here, like it is pointing this, it can only go here. Like, either it can go here, or it can flip omega 3, stay there, and flip the direction to here, or here, or here. These are the 3. This particle can only do this. It can move, because this site is vacant. It can move here. That is with rate R. R is this Monte Carlo rate. And it can flip, being there, like this, or that, or that. Change this direction.
So when you take omega to infinity, you also take some other quantity to either infinity or 0, so that some combination is finite, right? You got to do here?
No. Here we don't.
In the original model?
Yeah, it was there. Yeah, no, here directly go to, yeah. This omega is free.
So you don't have to...
You have to do it if you want to continuum limit. This one, if you want to continuum limit of this model, then you do it. Otherwise, it's okay. I have not done it here. Okay, so this model, omega goes to...
If you take the flipping rate to infinity, you also take velocity to infinity, and some ratio is...
You remain constant, yes. That you do this because you want a specific hydrodynamic form. I don't want to, no. So this is a free parameter, and omega equal to infinity, I know that this is just an Ising transition, I know it here. So now omega is equal to infinity is passive particles. So now I add activity in this direction, like in a small finite omega. So the question is that omega doesn't affect, which means the JC remains this. So if omega activity, how much time I have? Yeah, okay. So there are 3 possible things can happen. One is that it is just you put omega, it doesn't matter. So which means that earlier you need 0.88, that means that much of interaction. Now also you need that is the same interaction. That is one possibility. Second thing is that the line is like this, which means that earlier you need 0.8813, but now you need more interaction with activity. If you add activity, if you get a curve like that, which means that activity is not helping you. Right? You need even, with activity you need more interaction. So if activity helps phase separation, then the curve should be like this. That's what you expect. Okay? So you do the simulations of this for omega, and this is activity inverse. Is the other way. Inverse activity, this is this one. And you can see that, increasing activity or motility, it just doesn't help. So question is that, larger the activity, there is no such separation here. This inverse of this is 0, omega equal to 0. So which is that highly active things, it's less cluster. You don't have clusters there. So what we find is that j equal to infinity, this is 0.888, this line, it goes to, when omega goes to infinity, it approaches this line, but the line looks like that. So which means that for any finite omega, you need higher interaction, which means that it's not helping. This is completely contradictory to what people have been looking at, and that is a surprise. Yes, so here you don't get. With j equal to 0, you have a disordered phase. So we'll come to that, yes. So here something is missing. We do not know at this stage what is missing. And this transition is characterized by Ising transition. So we just take some order parameter and then try to figure out what is the transition, and three, four points we try to study. And this is my omega beta equal to 1/8, like that. So we characterize this phase transition, and we see that this is the correct one. This is not wrong. This is the wrong one. And there is no phase separation. In this situation, there is no phase separation transition at j equal to 0. Okay, so this is here. So now, no transition at j equal to 0. Okay, and now question is that no MIPS in absence of interaction. That's the question. What went wrong, or is it problem of slow coarsening and the simulation is a shorter time, or is it that problem with lattice models? Because was asking omega goes to infinity has to be rescaled with something else, otherwise you don't have a continual limit. What else is needed? Okay, so what we find is that we introduce more parameters. What we don't have here is that what you call positional diffusion. So you take the same Ising model or lattice gas, and those which are east, they primarily move to east, like with rate 1, it's extra rate, but with a small probability, it can also go to the other direction also. This is something which you extra add. You have a P now. And so earlier what I studied, P equal to 0 model. So now, if you take this model, and let us say j equal to 0 also you can set now. Now we'll study for j equal to 0. Okay? So this model, for P equal to 1, the direction has no meaning. If you set P equal to 1, all direction is the same rate, and j equal to 0. So it is nothing is getting from the interaction. Okay. So now the question is that for the model at P equal to 0, it is disorder, that we know. For model at P equal to 1, this is a simply symmetric exclusion process, so which is no transition. Right? I mean, P equal to 1 means there is no energy, a particle just moves left, right, everywhere with the same probability. So this is a simple exclusion process, it's also disorder. So now question that can it be ordered somewhere here? And it turns out that actually it does. Okay? So this side, it slowly, if you go here, this is a phase, there is somewhere in between P, you have a cluster state. And that is pretty surprising, even at j equal to 0. And that is probably the MIPS which we're talking about. So, and we try to, how do we study it is like we study percolation of this problem. Right? We study percolation, and this is the line which you get P omega plane at j equal to 0. So what we find is that when P equal to 0, there is no, this is completely disorder. It's a, right now, so basically if you increase P, initially it becomes an ordered state, and then with a larger P, it becomes disordered again. So there is a re-entrant kind of phase transition which is happening. And this transition is also characterized, and let us see so this is the way, so it's a re-entrant phase transition. And we try to get the order parameter, the critical points through Binder cumulant, and same kind of scaling we did, and we look at the critical exponents. But the critical exponents, all the points which we mentioned here, these points we study the critical behavior, and we find that critical exponent vary continuously.
But omega is very small.
Yes, that is where it comes. I mean, people who study MIPS transition, they know that very small.
That means that omega actually maybe becoming system size, small means system size 1/L.
Yes, it's probably that. Okay, so that is what we find here, that the critical exponent changes continuously, but there is one hint that, at some point it decreases, 1/nu decreases, but it becomes 1, like Ising thing. And this is a percolation study. So similarly, beta by nu also approaching the point 5/96, which you saw in interacting percolation. So we say that this might be a continuous variation from interaction percolation. Okay, so that is the hypothesis we take. And what we study is that we now look for, see, this is the exponent, how the exponents change, and that is the Z2 percolation. So it might be Z2 percolation superuniversality. Superuniversality, I will just define what is superuniversality. So this is just one page. So this is in 2023. So we just said that a system having continuously varying critical exponents form a superuniversality class X if the scaling function, we define what is the scaling function, remains invariant along the critical line, matches with the same scaling function of X. So what you have is that in this, the scaling function is the second moment correlation length versus Binder cumulant. Binder cumulant is a function of second correlation length, xi2 by L. Okay, U4 versus xi2 by L, and xi2 is defined by this. This gr is the correlation function. So here what I plot is that all these critical points which I saw there, like all the critical points, I calculated U4 by xi2 by L. This is in different points, different critical points. And the black curve is the curve I get from interaction percolation, which is the percolation of lattice gas. Percolation of lattice gas gives you U4 versus xi2 by L, this black curve, and all other curves matches with this. So the critical exponent at all the points are different, but this scaling function is invariant. Okay, so that is we call it.
Is this property valid only for some observable, for some quantities, or in general?
This is only for this quantity. Other quantities is scaled. The scaling function is the scaled form. You do not know.
It changes also with it because
yeah, it changes.
The way I calculate
yeah.
theory,
yes.
Is always a coupling around.
Yes, yes. So this is a specific one. This remain invariant, even though the exponents, critical exponent vary. This form, and that is a group of people. I think is from Rome only. We can talk about this. So this is all. They have also found it some QCD field theory. Okay. So what we find is that once we know that the percolation belongs to percolation of run and tumble particles on a lattice, two-dimensional square lattice, belong to Ising superuniversality class. So now the natural expectation is that corresponding MIPS transition, underlying MIPS transition must be Ising universality class. So you take some of the points which you study here, of this critical point, and some of the points we actually take that point and study MIPS transition there, phase separation transition.
This line, is it also the binodal line?
No. This is the critical line.
So the two densities will not be given by the points on the.
No. That is the critical point. So the density is still fixed. Density is half. The critical density is half. Okay. So this is the critical.
So it's about P as well.
It's a P. Yes, it's a P. So we'll come to this line, which was in the first page in my transparent. So we'll go there. So this is what we find here. And the transition belongs to Ising universality class, and we check at few critical points. So for few critical points, we also study, the order parameter for MIPS transition, phase separation transition, in some way. And this is the order parameter, and we find exactly this relation. So we know what is beta percolation, multiply by 12 by 5. We expect some beta, and that is the same beta which fits into the MIPS transition. So MIPS transition, I can see that, I have, from this, I anticipate what would be the beta, and with the same beta, the order parameter actually gives you a very good collapse. So this relation, percolation versus phase separation, holds here also in active matter. So now what I do is that I put P equal to fixed, some value, and study with interaction. And here, what you were asking, that the coexistence line I'm also plotting here. So for P equal to, this is P, which 0.5. Now I have interaction and density and omega. So, and the line which I was talking about is this line, which is the, this one. So this line is not exactly coinciding with rho equal to half plane, little bit here and there, but it doesn't matter because this is so flat here because we don't have any points there, so it doesn't matter much. So this is the line which I'm talking about. And these are the coexisting lines, density, coexisting density, a different J. Okay. So for J, with J also we find there is a line here, and this is very recent, last week. And this critical point is also, the exponents here varies continuously, and they also form Ising superuniversality class. Okay, so what we study is that when you study percolation, we study cluster properties, and when you study the same critical point, we study MIPS transition. We study like this, like take a rectangular lattice and study this. Here it's a square lattice. You study percolation. This is easier because the system size, small system size still works, and it's a better way of studying phase separation. This one, 512. Okay, so what we find is that P equal to 0, right? I mean, that is the phase diagram which I saw earlier. So for P equal to 0, interaction doesn't, activity doesn't help, right? Urna was also talking about this. So interacting system rather repels, right? I mean, and for J equal to 0, we have seen a transition that P equal to 0, there is no transition. And this curve somehow become this curve when P become very small. So you can see that it goes like this and come out like this. So it goes like this, and somehow a phase separated state appears here when you change omega. And so here also, if you look at the critical exponent along the critical point means here all along this, and we find that they're very continuously. And so again, this point, this line is again the CLG conserved lattice gas percolation. This is the line, and this is the different critical points on this curve, and they all fall together. So what we decide, what we conclude here is that MIPS transition belongs to Ising superuniversality class, and that MIPS in Ising class has been predicted by other people. And I think I'll stop here with it is my summary. I will not read it out. I will just rather thank Indranil, who is a part of MIPS transition and superuniversality class, currently here working as a postdoc. Abir is a student with me working at ISAR Kolkata, and this last work with interaction is done by him. And they are BSMA student. Their project thesis was part of this work. Like Kanti, Soumya Kanti is currently in Germany. Chandra Nivo is in Max Planck. Oiko is in Oxford. Birajit is in Warsaw. Yeah. So I stop here. Huh. Huh.
I'm 100% sure about it.
Leonard Jones, I never studied Leonard Jones.
But you have by mistake put Leonard Jones. I can show you here. And your 1/4 argument doesn't hold there. 69 divided by 4 is 0.4.
This is a lattice model. Leonard Jones is not the 1.4.
1/4, but it is Leonard Jones, I'll show you.
Okay, I don't know how, but I never studied, so I mean, it's a lattice model particle move on it. Yeah, okay, maybe. Yeah, maybe we can talk later. Yes. No, but I don't agree. No, the study is done by. No, the study is done by me. How can you say that what I studied? I mean, that is unfair, no? I mean.
Yeah, no, I'm a bit confused about the question that can MIPS happen at finite omega? I mean, can MIPS happen at finite omega?
Most people who study MIPS say yes.
No, your conclusion?
Yes.
Yes.
So if I understand correctly, you said for MIPS you need diffusion basically,
Yes.
right?
Positional diffusion.
Positional diffusion, and without that you will
You
not
cannot
get
have
MIPS.
yes.
And all these simulations, etc., people
No, they have
done
positional
like this,
diffusion.
all this
Yeah.
AB active Brownian particles, they always put diffusion.
Yes,
term?
yes.
Okay.
Because without diffusion, if there's the exact solution even in Martin Evans.
No, but that's
work.
two particle.
These are the two particles.
But two
then-
particle and
No. Let me say this. So with two particles, what you say that without diffusion, you have a delta function potential somewhere. And when you put diffusion, just 1 second, the delta function disappears. So the delta function makes the interaction extremely attractive, which makes a very small cluster. So there are particles there is very quickly they will form very strong clusters at different places. Without diffusion, they will not destroy. So
Yeah, I
even a
understand, sir.
micro-
But that's a 1D case, and 1D case is a pathological case, and we know that like it causes microclusters and you will not get MIPS, right?
yes.
But 2D cases without diffusion, you are saying
2D
that.
case also with the diffusion,
without-
the delta function will, without diffusion there will be
But
some.
they have many more ways to go, right? But you are saying that you will not get MIPS.
Yeah, will not get MIPS.
Okay, and even in higher dimensions.
Yes, in higher dimension. Yeah, that is the result, yeah.
3 dimensions.
Yeah,
Okay.
yeah.
Okay.
Yeah, but that is also like Aparna Bhaskar and some other people also studied that J actually, yeah, they have also found that, J equal to 0 and without diffusion you don't get it. Yeah. This is known to the literature. It is.
Small 2 particle cluster doesn't mean MIPS actually.
No. Yeah.
So, did you try to do like usual hydrodynamics and try to, like for this you should be able to do hydrodynamics, right?
No, here.
Why?
One can do, yeah.
Oh, you
have not
didn't do
done.
this?
No.
Because then you can predict this phase diagram and all, right?
No, I have not done it.
Okay.
Yeah, but one can study this, yes. Yeah.
Okay,
I've
and the
not-
other question was like, with diffusion you get a MIPS.
Yes.
And the Ising interaction helps it, right? I guess. You
No.
had a phase diagram, but I don't.
Yeah, no. So both ways. It is there are 2 zones, right? So interaction is here, like
Yeah.
first it goes down, and then it goes up. So this is this is the zone which is separate. So if you increase interaction this way, it is not MIPS goes down initially.
Oh, okay.
So this is the dome which separates the J phase plane.
Okay,
Yeah.
that's not obvious, right? It should have helped, MIPS in some.
No.
Like if you have a
Because-
more attractive interaction, it should have helped.
Yes. So for J equal to for P equal to 0, that's the phase diagram, and P equal to very small p, small diffusion, the phase diagram somehow goes down. So P is a singular perturbation to the problem.
Okay.
You see, it's not perturbative. From here to here, it's not perturbative. So something strange happens. P equal to 0 is a very special case.
And your interaction is only in the density. There is no velocity orientation here, right?
No, orientation I'm not putting anything. Orientation is everything is everywhere, yes. There is no orientation in interaction. Yes.
Yeah, this one.
So one can imagine slightly more complicated diffusion processes like what Kraus studies, this lifted SCP or lifted exclusion processes where the things have a little bit of persistence. That changes the diffusion. Will it also change the critical point?
Critical point, yes, I think, but not the exponent. I do not know.
I see. Okay.
Because exponent is already, right, somehow there is a marginality, and I have a guess of where does this marginality come from. So now what happens is, why exactly this continuous variation? Why should you expect in MIPS there is a continuous variation? Is that when in 1D you know that they block each other, and that is that the blocking, J equal to 0, the blocking is the only way things get interaction. So now to get a interaction like that, 2 particles which has to be together, so that is Ni plus 1, times some way you have to say that the spins are like this, then they will block. So the interaction depends on Ni and Nij, Si, Sj. So that is if you separate it, just Ni becomes Si plus some tau I plus 1 by 2 or something. So tau I tau j Si Sj, which is like a Askin-Teller interaction, and which is marginal, and that is the marginality which is coming there, I think.
May I add something to that?
Yes, please.
Is it like frustrated system of a spin, but with 4 spins? So it goes from ferromagnetic order to endoferromagnetic order, just for a 1 square like this. Would you say yes to that?
No. Sorry.
Okay, so let's thank PK once again, and then our next speaker is Vijay Krishnamurthy from ICTS Bangalore.